computed. Okay, so let's continue. Welcome back to our lecture, second to the last lecture of neural networks. Artificial neural networks, excuse me. So we say that artificial neural networks is based on the model of the brain neurons and how they communicate with respect to all the other neurons. So that is basically the motivation or the inspiration on coming out with this algorithm. So what we discussed previously was this activation function that triggers the output, the output of the neuron, you know, that goes into the axon, and then the communication, the values that brings the output of this neuron, okay, and give it to the other neurons. So now we consider only the simple perceptron function, and we come out with the algorithm in order to update the weights. But then today we're going to discuss about another function, sigmoid function, which is the usual way, the usual activation function that is being used for most neural network systems. Okay, and we can see what happens to the update of the weights. Okay, now so let's go to the weights update. So this is the perceptron, and we use this activation function. Okay, so we sum up all the weights and the inputs, and if it's greater than 0, the output is 1, and then it's less than 0 or otherwise, okay, greater than 0 or less than or equal to 0, that's -1. Okay, so we say that that function can do linearly separable data, so that's fine, but it doesn't work on the non-linearly separable data. So, but then let's work on it and see how do we optimize the result. Optimize meaning compute for the weights. So this is the weights that our inputs are computed from. So this is the perceptron where you have input x1 to xn, and you multiply them with certain weights. Okay, so this is the bias multiplied by the weight W0. And then we just sum up Wi times xi. We sum up the product of the weights times the inputs, and that is already our, am I clear? Is the voice clear? Okay, I'm hearing feedback, but anyway, so this is the summation of the weights times the inputs, and then greater than 0, then the output is 1, we output 1, otherwise we output -1. So that's the perceptron, and we know that to compute your weights, to compute for the updated weights is this one. We spend a lot of time saying or trying to explain that the weights Wi, okay, updated by the current Wi plus the correction of delta Wi, and delta Wi is multiplied by okay, let me open that picture so that you can, the picture of the data that we used before, so that you can be more, okay, this one. Okay, so if that is our data, so we say here you have the output, this is the output or the target value, and then inputs of x1, x2, x3, x4. And then you have data for the first instance of experiment of reading, for example. This is temperature, I think, and this weight, or no, what is this? Meters per second speed. And this one is volume. This is in liters, or what is this? Yeah, something. So these are physical parameters, and these are the outputs. So we take each data. So one point of the data, another point, another set, one set, second set, and third, and so on. And so we say that your target value, this is the target value, and your output is computed from the output, this one, the output equation, where your W0 multiplied by the input, the summation of this, that's the output. So the target value is from the table, and then xi is the x, that particular x that you're considering with respect to the ith W. That means W0 or W1 or W2 and so on. Okay, so which X corresponds to that one? So is it X1, X2, X3? So if it's W0, then it's X0. X0 is 1. Okay, if it's W1, then it's X1. X1 is this value. So whenever you compute this, you look at the table. So this is the X that is on the table, the input on the table. T is the output on the table, and O is the computed output. Okay, then that's how you update your delta W. Okay, I think that is, I hope that is clear now. So now let's go to, we don't need to do, let's go to the sigmoid. Okay, now in the sigmoid function, you just change, instead of just the normal W xi, wi times xi summation as your activation function. We don't do that. What we do here is we use this as the exponent of e. Okay, the exponent, the exponential function e. So e to the power something. So now we, instead of just the summation, previously we have our activation function was only, okay, was only equal to net. Okay, now our activation function changes so that, okay, it becomes that. Okay, the net is the exponent, where net is equal to the summation of wi xi. Okay, you understand? So this is what we say the perceptron, which is the perceptron function that we did before. Now the other one is sigmoid function. Okay, so that's the only difference. So now, okay, everything else remains the same, especially in terms of how we take the gradient to come out with the optimal value, to come out with how we are going to compute, to update the weight. So now this is your gradient of E. Gradient of E. This is the function, okay, which is equal to that one. Let me remove this. Okay, now this is the partial of E with respect to Wi. So gradient of E with respect to Wi, I think we can do that. With respect to I. So now we are going to compute this for all W's. That means gradient of E with respect to W0, gradient of E with respect to W1. All we need to understand is this one. So there is a good property of this sigmoid function that makes it the popular choice of many. Okay, so one of the good property of this is that the derivative of this sigmoid function with respect to x is this. So now this is the original sigmoid function, and its nice property is you take the derivative with respect to x, it is just sigma x as it is multiplied by 1 minus sigma x. Okay, so this is the strong property of this, nice property of this sigmoid unit that gives us, a better, more manageable way of looking for the optimal solution. Okay, so now because of this derivative, let's see what happens. So now, okay, so because of that, so it's coming from here. So the partial of E with respect to Wi, because of the simplification of the partial of the output with respect to the net like that, so it becomes just output because it's coming from here. Okay, the output times 1 minus the output. Okay, that's the derivative. So we are just going to substitute it here. The output multiplied by I minus output. That's that one. Okay, and then you have partial of net with respect to W partial of Wi. A partial of net with respect to partial of Wi, which is XID. So XID there, that's that one. So now we repeat So see this part, okay. Okay, so because of the nice property of the derivative, so we rewrite this part into here, okay, there, and this one on this part is that, okay, which is this one, output times 1 minus output, so that's that one. We just exchange that, I mean we substitute that. Now partial of that with respect to wi is that we know this xi, we have derived it before. So oh no, the net is, this is partial of x with respect to, net is w times x, so w times x of the data. And so if we take the partial of that, so with respect to wi, then the result is just xi. We have manually computed this before. So now your partial of v with respect to wi simplifies to this form. So this is the major motivation of that, one of the biggest that contributes to the ease of computation on the sigmoid function. The derivative being a lot easier to handle. So now let's continue. So all we need to do here is, there are 2 steps here. So all we need to do is that, okay, let me show, this is not very efficient way. Look at this picture. Do you see this picture? Or is it small? Maybe I should make it big. It's too small for you. Okay, let me, because for me it's big because my computer, my screen is big. So here, so let's consider this. In this example, in the class and in the test, okay, we are only going to consider 1 input layer, okay, 1 hidden layer, and 1 output layer. That's it, okay? Because I only want you to understand how things are computed in this way. We are going to do back propagation, okay? Back propagation meaning we compute forward, and then we update the weights of this W1, the weights of the W's as well as the weights of the V's, okay? So that in this case, we can update the W and then compute again. So it's a recursive process where you take the input and then use whatever random values you have for the weights, compute the output, and then based on the error of the output, you are going to back propagate and update the W's. Okay, update this value of the W's, and then afterwards you get the new values of these W's, and then you back propagate based on that one. Then we will know what is the value of your Z, which is the corrected output of this layer, of the hidden layer. And now we back propagate to update the weights of the V, and then that's it. And then compute again forward. You do these inputs with new updated V, compute the output Z, and then multiply the updated W, and then you compute the output, and then back propagate. So like that, forward and backward, forward and backward, forward and backward, until the errors that you see here in the output is being corrected and becomes much, much smaller, so that now whatever weights you have here for the W's and the V's are the ones that we are looking for. So you understand? So all we need to do is look for the values of the weights, these weights, okay, and the values of these weights. Okay? You understand? Okay. So I don't want to go into much more complicated structures, but this is done so that we will have the exercise of computing on how things are manually computed using pen and paper, so that we can come out with the updated weights that will have lesser error in terms of our output. Okay, now that is, I hope that's clear. So no, okay, let's go up. So now these are the steps that we are going to use in order to update the weights. Okay, so these Okay, we will explain later, but these are all the formula that you need in order to update the weights. As you can see, okay, in this case here, the last weight that we update is the W. I mean, is the V. So that V is the weight, the weights of the input parameter, okay? Because we are going to do back propagation, okay? So here, the next last weight that you update is the weight of the hidden layer, okay? These weights, and then eventually on the output. So here, we are going to correct here based on the delta W, I mean delta K, where your delta K with respect to the outputs will be just this value that will be used in the updating of delta W. Okay, so just bear in mind that these are the equations that we're going to use, starting from the output, target minus the Y, that is the computed output, which is we represent it as O before, but here is Y. So anyway, Y minus a target is from the data minus the output, and so on. And then you update this delta K, and then this delta K is multiplied by WKG, where this is the output. This is in the output layer. Okay.
So
Yes.
what is a delta K again?
Okay. Delta K, this delta K is used here to multiply to this one. Okay. I mean, you can just multiply all this to here, but it's just represented as this one so that you will multiply it with the WKJ, which is the weights of your hidden layer. Okay, multiplied by this output. And then now, this is the input of the hidden layer. Okay, and then we update the delta J. So delta J is somewhere here that is being used also here. So anyway, so what I'm just trying to say here is that from the output layer, you update the weights of the hidden layer, and then now when the hidden layer is updated, now the next thing is to update the weights of the input layer. So this is the weights of the input layer, which we will update. So in this case here, you correct first the target minus the output. So here, this is the output, which is Y. This is the output. This is the output. Okay. Weights times whatever X, whatever the input X is. Okay. I think there's something wrong here. It should be Z, I think. Because this is the input, it should be Z. Okay, it will be clearer in the example. So I think this should be Z, because in this case here, for example, if we only consider this as the sigmoid function, and these are your weights, and then this is the input. The input is Z in this case, Z0, Z1, and Z2. Okay, but here, where your output is Z1, Z1 and Z2, and your input is X. So now this is the one, X, X0, X1, and X2 multiplied by V1 from here, okay, multiplied by V1, and then you have another V2. So V2, because your input is X2 multiplied by V2, this is V2 and V2, V2 first component, V2 second component. In this case here, V1, so V1 first component, V11, and V2 second component, multiplied by the input. So it's always like this. This is the output. Okay, the sigmoid function is like that. The output, and this is the input, multiplied by the weights. Okay, so that's why here this should be Z. Okay, this should be Z because the input here is Z. Okay, multiplied by the weights. Okay, and you have the Y output. Okay, so now, so the weights are updated like this, so that you know when you have in the hidden layer weights, these W's. Okay, well, I prefer to say the weights of the hidden layer. Okay, it could be the weight, we can say that weights of the output layer and weights of the hidden layer. But anyway, this is the weights of the hidden layer. Now you have This is how you update. We already computed this before. So when you use these equations here, we are saying that this is already the way, this is the function of the gradient. Partial of E of the error with respect to partial of the weights, okay, J. Okay, so we don't need to go through the derivation again. What I'm saying is that once you use these equations, this is already the gradient descent function that we have already previously derived, and so we can use them in order to update the new weights. Okay, once this weight is updated, okay, now we can use these weights to update. This is the weights of the hidden layer. We can use these updates of the weights to update the weights of the input layer. Okay, so we update the weights of the hidden layer, we update the weights of the input layer. Then we go back here. We go using those new weights. Okay, we go back. What is the value of the Z using the new weights multiplied by the input, and then of Z1, and then of Z2, and then of Y1, and then compute back. Okay, it's like that. Okay, so move forward first. This is the forward movement of forward computation, and then backward computation by updating your weights, and then forward computation to check what are the outputs, Z1, Z2 output, and Y1 output, and then go back to update the weights. That's all. It will be that cycle. Any questions before we go to the example? Okay, so I want to emphasize that there are two ways. So by the name of back propagation, this is forward computation. Okay, forward computation to compute the output, and this is the backward computation. Backward computation to update the weights. That's all. If you understand this, then that's it. All we need to do is just substitute the equations, substitute the values, then we're done. That's all. It's just tedious, but the concept is this. Okay, so in our computation, we use the sigmoid function. We don't use the perceptron function because that one doesn't, so it's only applicable to linear problems. But we are looking at, for example, the XOR. It cannot be computed, it cannot be solved. But here in the sigmoid and +1 hidden layer, then we can solve that problem. Any questions in this one before we continue?
Yeah, I was wondering, so if we're doing backward propagation, how far back do we go? Like, do we go into the input layer and the hidden layer? So do we update the V's and the W's in one iteration? Like, if we're going backward, do we update both the V's and the W's, or just one layer?
Okay, Mr. Mopate, I want to see you. You turn on your camera. Okay, yeah, it's a good question.
I have to travel to school.
You have to travel to school, but you can attend class anywhere.
Yeah, the Wi-Fi in my room was very bad, so I had to go to school.
Okay, that's fine. So now this is what it is. So that's a good question. So in back propagation, what we really want, but in all other computations, what we really want is we want to know what are the optimal values of the weights. Okay, we want to know what are the optimal values of the weights so that we can classify or we can get the proper output. Okay, for example, an output of 0 and 1. Let's assume. Okay, 0 for certain characteristics and 1 for the other characteristics. Okay, so we want to know Well, in our case, initially, we don't know what's the correct value. So we randomly assign those values of the B's and the W's. Okay, that's fine. But then how do we correct them so that we will know we will be moving towards the optimal values of those weights, so that eventually, after certain time or after several iterations, our weights will be finally corrected. Okay, and then moving closer to the optimal values of weights, so that eventually we can come out with the correct classification of these 0 and 1 classification. You understand? Okay, that is clear. Okay, so again, I want to emphasize that our computation here is geared towards looking for the optimal values of the weights. Just like in all the other computations that we did before and all the other methods that we did before, the same thing in neural network. We also need to compute for the optimal weights. Okay, the only difference here is the architecture on how the solution is being formed. The architecture here is in terms of the neural architecture, just like the human brain architecture. The other one is like a decision tree, it's like a tree. Okay, the other one is, the other one is how do we, well, based on error for a polynomial, it's a polynomial function like that for linear regression. Okay, so like that. So now, because here we are modeling neurons, so the inputs and the output are modeled this way, and we are using this sigmoid function. Okay, so now there are two ways of computing so that our weights will be corrected. So one way is moving forward. Okay, moving forward meaning we use the inputs don't change. Okay, because these inputs are our experimental values. Yeah, so we use those inputs. So this is the bias. So there's always one. There's always a bias one. So in this case, there's the experimental inputs are x1 and x2. Okay, so these inputs we use the current weights. Whatever random values of weights we use, then we'll come out with the z value. So that's why here, yeah, you have the input x and the output. I mean, the input x multiplied by the weights v1. Okay, then you have an output z1. Okay, then the output z2, you have x1 and x2 multiplied by v2. So multiply x1 multiplied by v2 and x2 multiplied by v2. Okay, so v2. So I think here again there's something wrong in the labeling. Because it will confuse you later. Okay, let me be very, very careful here. So your x, we know that your x is x0, x1, x2. Okay, those are inputs. So I hope this is clear. I think that's very clear. And x3. Okay, now let's talk about z1 output only. Okay, so if this is your z1 output, you have input x0, input x0, input x1, and input x2. Okay, so it's multiplied by the weights v1 vector. So there's a v1 vector. This input, outputting z1, you are using a v1 vector. That means that you have v1 0, v2, v1 1, and v1 2. Okay, so all components, these are components of v1, so everything should be v1. So v1 0, v1 x1 times v1 1, and x2 times it should be V12. That's why there's something wrong here. Because it's going to that one, so it should be V12. Okay? Because the Z1 output corresponds to a V1 weights. So V10, V11, and V12. Okay? Multiplied by the corresponding X0, X1, and X2. So I hope that is clear. So now let's talk about Z2 axis. So for Z2 axis, the same thing. You have inputs X0, X1, and X3, and then the weights are V2. So in this case here, V20. Okay, this is this V20. So input X1 should be V21. So this is V21, and then input X2 is V22. Now it's correct. So this is the one that was interchanged. Okay, so now we are clear about that. So now our output Y1. So our output Y1, we have weights W1, 0, W2, and the W1, 1, and W12. So your input here is the Z. So that's why this one, it should be not X, but Z0, Z1, and Z2. Okay, so Z0 multiplied by W10, and Z1 multiplied by W11, and Z2 multiplied by W12. Okay, so that means in this case here, it will be, you multiply this with W10, W11, W12, there, multiplied by this one. You understand? And then it gives you the output Y1. Okay, I hope this feed forward is clear. Okay, so there are two mistakes in the slide. This one, let me take a photo so I can correct this. Okay, so now this should be a Z instead of an X, and this one should be V21 and V12. Now, so I hope this is clear on the feed forward. Okay, you given the input, you get the output. Input X, output Z1. Input X multiplied by weights V2, output Z2. Input Z multiplied by the W, output Y1. Is this clear? I hope this is clear. So now, okay, this is just feed forward because we want to compute the output. Now, we want to correct the weights now. To correct the weights, we want to know what is the error between the output against the target value. Okay, remember, this is the essence of the gradient, the partial of the error with respect to the partial of the weights. Okay, so we don't need, so these equations here is equivalent to this one. Okay, so we don't need to worry about it. All we need to worry is just now substitute, because we dealt with this one already. Now we only need to substitute. So what is YK? So we only have one output here. So this is Y1 and Y1 and Y1. That's it. Okay. What is, so in this case here, K is 1. Okay. We only have one output. So K is 1. Okay. So now what is J? So J, you remember you have J10, J, this is W10, W11, and W12. Okay, so what is ZJ? So depends on what is your W. If you're looking at W10, then it will be Z0. Where is Z0? This one, this is Z0. The bias. Okay. This one is X. Okay. Okay, this is X. 1, 0. Yeah, this is x. This is x0, the same. That's x0. This is also x0. This have the same value, 1. Okay, it's just multiplied differently by, it should be, I mean, there should the same thing. There should be 2 arrows here, but because they are drawn like this, so they are 2 separate things, but they are the same, x0 and x0. Okay, so in this case, that is z0. So now if you want to compute for w11, the same thing applies. Okay, target output is the same. This one is the only one that will change. It will be z1. So what is z1 here? The value of that computed value from here. Then w12, change it to z2. Okay, but those are computed from here, so you just substitute, finish. Okay, so now you were able to update w10, w11, and w12. Now again, the same formula or the same process of partial of E with respect to now V. Okay, maybe you will be dizzy, but don't worry about this process anymore because everything is computed for you. So all you need to do now is a substitute here. Okay, so you update your weights here, W, and then you update your V also here. In your case here, you have V, J. Where is J? Okay. In this case here, you have how many components? So you have V1, okay, and you have V2. Okay. So now if you go for each component, the V1 and V2, so V11. So the same thing here. So and V12. So for example, if you are doing V, okay, maybe let me delete this one here. So remember, we are going to update also V1 and V2. So here we have already updated all the W's. And then we also need to update here. That's why, because it's back propagation. Once we update here, once we update the W's, because from the output layer, we correct the output against the target. We correct it, we correct the W's. And then now from this, we correct it based on the error now between the output and the target and the weights that we have computed previously. Okay, and then now we will compute basically what this one means, that the output of the Z1 is also corrected, and then we update the V's. Okay, to update the correction on the Z1 and Z2, this is how we are going to do it. So if you are doing V, okay, V11, so the same thing, that's B11, whatever B11 is. So remember the J here. The J is for the first. So this is V1. Okay. So this is Z1. Okay. So this is Z1. So and so on. You just compute. Okay. K, this one K, this is from K. Okay. K starts from 0 to n, but because we only have one layer, one output. Now here, this is only one. So we can, for our case, we can disregard the summation because we only have K is equal to 1. So just compute it directly like that, and then that's it. Substitute. No issue. Okay? We concentrate only on this architecture. Don't think about other things. I just want you to understand this architecture only. Oh, it's 2 o'clock. Okay, let's, I think we can finish everything today. Okay, let's have a break, 10 minutes break, and then we'll come back at 2:12. Before that, you have any questions so that I can address them? Any questions?
It's fine.
It's fine. Okay. That's why I just warn you, it's just a little bit tedious. But once you understand these, especially the indices, the I and the J, and it's just all about substitution. Okay? Okay. Let's have a 10-minute break and then we'll come back. See you.